Hey, geometry. Welcome to week 7 of distance learning. So, this week we are talking about probability still. That's what we're going to be talking about until the end of the year. We've actually only got like 1.5 more weeks to go, so congratulations. You're really close to the end. But this week in our probability quest, our quest to figure out how probable things are, we are looking at a specific display of data called a two-way table. And within that two-way table, I forget I have this tool, within that two-way table, we will have two different kinds of probability we're going to discuss. We're going to discuss something called conditional probability. And then in the next video, I'll give you a bit of a pause this week, but in the next video, we're going to talk about things like the intersection and union within a two-way table. So the two-way table is going to be how we display that this week and how I ask you to read that. But then we'll be talking about conditional probability, intersections, and unions. So let's get started. A two-way table is a table that organizes data or categories of items so that they can more easily be compared to totals of the categories or totals of all items. They are just a handy visual, They are a handy visual organizational tool to just show a sample space and calculate some probabilities. So, our first problem is to use the information given in the two-way table. So, it says in a survey of 100 people, so we have a total of 100 people, 45 were 21 years old. Or older. Sorry. So here, let's do some highlighting. 100 people. So that's the total of the total. That's everyone. So that's how I read this. It says that 45 were 21 years old or older. So I'm going to look at the 21 or older section, and I'm going to look at the total. So the total is going to be 45. 33 were 21 or older. Whoops, I already used red. And, gosh darn it. 33 were 21 or older and drink coffee. So how I read this table is it has to be in the 21 or older section, and it has to be in the drink coffee section. So I look for where those overlap, which is right here. So this is the section where they are 21 or older and drink coffee is right there. So 33 go there, apparently. And lastly, we have, nope, I already used red. We have that 30 were younger than 21, so that's this section, and do not drink coffee. Does not drink coffee. So our intersection there between younger than 21 and not drinking coffee is right here. So there are 30 that go in there. So that's the data the problem gives us. And it asks us to fill in the whole two-way table. So now I look at it and I go, what? A little bit confused. And I think, okay, wait a second. I think I can fill some of this in. So if I know that there are 100 people, and I think, okay, people are either 21 or older or younger than 21. You can't be neither of those. So that means if there are 100 total people, 45 of them are 21 or older, that means that the other 55, that's 100 minus 45, just draw an arrow, that means the other 55 are younger than 21, right? Because you're either older than 21 or you're younger than 21. Those are kind of the two options. So those should add up to our total number of people. Okay, now I look at something else. Let's look at these. Out of our younger than 21, this column, I know that 30 don't drink coffee. So if 30 out of 55 don't drink coffee, that means 25 do. Then I can go ahead, same idea here. If 33, 21 or older do drink coffee, then 45 minus 33, or 12, don't drink coffee. Then I'm going to add up my totals to get these. So this is going to be the total. This I read as the total who drink coffee. This is the total who don't drink coffee, not caring about age. So we have 58 coffee drinkers and 42 not coffee drinkers. And here's a chance to real quick check my work. Those two add up to 100 is a good sign. So that's how we'd fill in the two-way table. We think, okay, what did the problem give us? And then how do we use these rows and columns? It's almost like a Sudoku. How do we use these rows and columns to find the missing pieces? So that is just the two-way table. So that was the first part. Done. The second part is looking at something called conditional probability. A conditional probability is a probability that compares an outcome to a particular subsection of a sample space. So this means that we're not looking at the whole sample space, we're looking at a subpart. And to use conditional probabilities in symbols, we say that P, the probability of A, the word that we look for is given. So the probability of something given something else, A given B, is the same as, this is writing it the same different way. Probability of A, and then we have this line. This line means given B is equal to the number of people who are A and B, or the number of outcomes that are A and B, divided by the number of outcomes that are B. So this is all formal mathy stuff. Let's look at it in our example because that might clarify it a little bit. So for the example above, instead of looking at coffee drinkers younger than 21-year-olds compared to the total amount of people, we could compare to just the coffee drinkers. So if I want to know the probability that someone is younger than 21, given that they drink coffee. So I'm investigating, maybe I'm, I don't know, let's see, what's a local coffee company? Dutch Bros. I'm Dutch Bros. And I'm trying to figure out, okay, who do I market to? Do I market to people older than 21 or people younger than 21? So I'm saying, okay, of coffee drinkers, what's the probability, if, I serve 100 coffee drinkers in a day, what's the probability how many of them are likely to be 21? So what you do is you take the number of people younger than 21 and drink coffee and divide it by the total coffee drinkers. Oh, except my program's going to shut down. Give me a second. So you divide that, so the number of people who are both younger than 21 and drink coffee, and you divide that by the total number of coffee drinkers. So I want to actually look at that. So the number of people who are younger than 21 and drink coffee is 25. But the total number of people who drink coffee in this scenario is 58. So our probability is that 25 out of 58, 25 out of 58 coffee drinkers are younger than 21. So this is read that the probability, if we read it above, this is read that the probability that a person picked at random is younger than 21, given they are a coffee drinker. So given that they're already in this subsection, that's the 58 coffee drinkers. Right? We're not looking at like 25 out of the total. We're saying it's 25 out of just this row, the coffee drinkers. So, the fancier definition, because that wasn't, fancy enough, is read: conditional probability is the probability of an event occurring given, I forgot my E, that another event has occurred. Or you can think of it as the intersection of two characteristics divided by the total of one characteristic. That's just jargon to confuse people, basically. Or I can think of the denominator is the total number for the given condition, which is right of the line symbol. So I think sometimes what I do to kind of help myself out is I kind of take it, so it's it's the probability of A given B. I think of this as this given kind of turns sideways, and it's the probability it becomes divided by B, right? It kind of like rotates sideways. But then the issue there is it's not just A on top, it's A and B on top. Goodness, I'm not connecting well with my pen. So, it wants us to fill in the following two-way table and find the probability of the following numbers. So it wants us to fill in the two-way table and then investigate some things. So, first, sorry, my pen's working again. Let's fill in the two-way table. Okay. So, males. The males in this study, there are 90 of them. 19 have pierced ears. That means 90 minus 19. Or 71 don't. Then I go, okay, I kind of know nothing about the females, but let's use some of these things. I know that of people who have pierced ear, only 19 are male, and there are 103 total. So that means, sorry, this is a bit, this two-way table is making assumptions about gender being binary. But in this two-way table, we have male and female people, and so our assumption is that those who are not in this category in the survey would be in this category. So that would make, if there are 19 males, there would be 84 females. And if there are 71 males with unpierced ears, there would be 4 females with pierced ears. And then we can discuss, well, that means there are 88 total females. All right. So then I investigate my probabilities. So, the probability that someone in this survey or whatever it was is female is going to be how many of them are female. Well, 88 of them are female. So those are the female outcomes divided by, and this isn't a given, so this is the total sample space. So 178. And then from there, we simplify our fraction. I know I can divide by 2. $89, and I don't think I can really go any further than that. I think that's as simplified as it gets. Someone can correct me, though, if I'm wrong. So, that's the probability you're female, or that the people in this survey are female. The probability that someone in this survey has pierced ears, well, pierced ears, the total, we have 103 people with pierced ears out of 178. So they're not divisible by 2, or by 3, or by 4, or by 5. I'm going to try 7. I'm going to try 13. I think that's as simplified as it gets. Maybe I did something wrong, but I think that's it. So the probability someone has pierced ears is 103 out of 178. Now here come our conditional probability problems. So this is saying, what's the probability that a person, according to this data, is female given that they have pierced ears? Well, how I think about it is I can think about it a little backwards. I start with how many people have pierced ears. Well, 103 people have pierced ears. And so then I think to myself, well, out of those 103, how many of those are female and have pierced ears? 84. 84 out of 103. And I'm getting a little off. Is 103 a prime number? I feel like it's not, but I can't think of what its factor is. Oh, nope, 103 is prime. So that makes my life easier. So since 103 is prime, I know that this is the simplest form. So 84 out of those, given that you have pierced ears, 84 out of 103 will be female. Is kind of the thought process to that. And then, given that the person in this data is female, so there are 88 females, 84 of those had pierced ears. So 84 out of 88 have pierced ears, given that they are female, right? Because here's total female, and here's female with pierced ears. Female and pierced ears. So you divide those, then we seem to have a fraction simplify. I can at least divide by 2. I think I can divide by 4. So that's going to be 21. That's going to be 22. And I think we're good. Simplified fraction. So, that's our first example of conditional probability. Now this one, you might want to copy down the table and fill out yourself. So, this is about, and this is something that's super commonly used with various medical tests, which is there are things called false positives and false negatives and things like that. And the point is, if you test positive but don't have the disease, that is a false positive. That means that whatever it is, the test, says you have this, but you didn't. And so then they're going to use treatments on you that might not be necessary. Or maybe there was some underlying other condition that was causing it, and they're not aware of that. Whereas over here is what's called a false negative, which is you have the disease, but the test didn't pick up on it. So, you have a disease, but the test completely misses it. So, yeah, so those are two different things, false negatives and false positives. They're both not great things in the medical field. You don't want them to happen. So what this conditional probability is looking at is kind of some of the data around that for whatever disease this was and whatever test they were applying. So it's asking for the probability, and you can try this on your own if you want, or you can wait for me, or try it on your own, pause the video, and then check your answers with me. So the probability that it is a positive result given you don't have the disease. So, how many people did not have the disease out of this survey? 620. So 620 did not have the disease. But out of those 620 who don't have the disease, 62 of them got a positive result, meaning doctors or whoever thought that 62 out of the 620 had the disease. And then if you actually simplify that fractions, that means 1 out of 10 patients who didn't have the disease were thought to have the disease, which that's a pretty big number. Whereas so that's the chance of a false positive on this test, right? They did 1,000. That's a reasonable size sample size for a medical test, because it's hard to get, it's hard with a lot of diseases to get 380 people with the disease. But yeah, so 1/10, 10% of the people who don't have the disease seem to test positive given this test. And how many people got a negative result who have the disease? So how many people had the disease but it kind of missed it, the test missed it? Well, this one looks like it's going to be better. Oh, what's happening? Except I can't use my pencil. So, how many total have the disease? Well, if I look how many total have the disease, well, I guess I'm just going to say it for a second. 1 second. Close it, open it. How many total have the disease? 380. Of those, how many tested negative as if they didn't? 19. So 19 out of 380 got false negative, so that means they had it but it missed it. And if you look at that, that's simplest form because 19 is a prime number, but I'm gonna round, if I round to 20, I don't know. It's a much better result. So it's more likely to say that you are positive when you don't have the disease, which is less worrisome than if it says you aren't positive and you have the disease, because that just means they missed it and they can't start whatever treatment or whatever you need. So that is what I wanted to cover on conditional probability. The probability of this given this. So go ahead, take a break, take a walk, stretch, do whatever you can to clear your mind so that you don't have to listen to me ramble for however much more without taking a little bit of a break, and I'll see you in the next video.